So in the previous video, we looked at the effect of surface orientation on the pressure. Now we are going to take a look at the dependence of the pressure on space. In other words, does it vary with x, y, and z in a Cartesian coordinate system. So now we are going to look at the pressure field P as a function of x, y, z. And in general, this could be an unsteady pressure field. We aren't going to look at that in this course, but in general, it could be a function of time. So what we are going to do now is, well, we are trying to answer the question, how does P depend on space and time? In other words, what is the equation for P? So it's a very similar exercise that we go through. We take a coordinate system, x, y, and z, and we take a differential element that has sides delta x, let's see, delta x, delta z, and delta y, and we collect forces in all three directions. This time they are all angled, they are all aligned with the coordinate system, so there's no theta coming in. And if I said that my pressure at the center is the P that I'm looking for, and in general pressure now is a function of space, so if I looked at, let's say, the two pressures acting on opposite faces that have their normals to the y direction, then I would say that the P on the right, PR, would be P plus del P del y times delta y by 2, right? That's a distance of delta y by 2 away from the center, and I use the partial derivative to account for that change. And P left would be similarly P minus del P del y times delta y by 2, because I'm going in the negative direction by a distance delta y over 2. So if I were to now take the total force acting in the y direction, that would be summation Fy. This time we'll retain an acceleration term and we'll say that's Ma, which in this case would just be May. So it's just M times Ay, which would be rho times delta V times Ay. Let's write that out in full. What we are getting is, we are looking at forces in the positive x direction, y direction. So that would be P left minus P right times the surface area, which would be delta x times delta z. That is equal to the mass times volume times acceleration. The mass would be the density of the volume times the volume, delta x, delta y, delta z, times the acceleration Ay. So that is P y minus del P del x times delta y by 2 minus Py minus del P del x, oops, that should be a delta y here. And so my pressure itself cancels out. What I'm left with is minus del P del Y times delta Y delta X delta Z is equal to rho delta X delta Y delta Z times AY, or minus del P del Y equals rho AY. That's in the y direction where there is no gravity present. Let's redo this for the z direction. So for the z direction, I am going to say that my differential element has two pressures acting, one from the top, one from the bottom. And so P bottom would be P minus del P del Z times delta Z by 2 times delta, just that. And P top would be P plus del P del Z times delta Z by 2. Those are my two pressures, and now when I balance forces, I have got to take care of the weight of the element as well. So I get summation Fz is MAZ, and this would give me going in the vertical direction, P bottom minus P top, that's P minus del P del Z times delta Z by 2 minus P minus del P del Z delta Z by 2 that's the force acting in upwards minus the weight of the element, which is rho delta x delta y delta z times g. That needs to be equal to MAZ, which is also rho delta x delta y delta z times AZ. And so I get minus del P del Z times delta V equal minus rho delta V, G is rho delta V AZ, or minus del P del Z minus rho G equals rho AY. So I could look at my equations in the x direction, which says minus del P del Y is just rho AY, and here minus del P del Z is rho AZ, that's Z not Y, plus a correction term for the fluid element's weight, which is a minus rho G. So we have the two equations for the two directions. I'm just going to combine them in a form that takes care of all three directions by just writing minus del P minus gamma K is rho A. And this takes care of all of that, because this could be written, this is of course a vector, the gradient of the pressure is the scalar field, gradient of P is the vector corresponding to which has the three components of the pressure gradient. We know that in general, if I were to write del P would be a vector that looks like this, del P del xi plus del P del y j plus del P del z k. So this equation in the box here is really three separate equations for the three directions rolled into one. So if I were to write that out separately, minus gamma k, where gamma is rho g, would show up only in the equation in the z direction. For the other two directions, the equation would have no gravity, it would just be minus del P del x or minus del P del y equals rho ax or ay. So you can expand this out, but this is the general form of the equation. And what this lets us do is we have an equation now for the pressure derivative, pressure gradients as a function of gravity and density. So we can handle odd situations, like for example a case where density is changing with respect to space, and that's not so odd. If you wanted to, for example, find out what the pressure field is in the atmosphere starting from sea level and going up in the atmosphere, we have a situation where gravity is more or less constant but the density is continuously changing. And so one could integrate this equation in order to get that final variation of pressure. Similarly, we could think of things like let's say regions where there's in the sea where there's excessive salt concentration, and so there's a slight gradient in density, and so one could look at how the pressure would vary in the ocean as a result of salinity gradients. And of course, if you were interested in, let's say, a planet where the atmosphere has a gravity that's very strongly changing as a function of height, probably because of very strong density gradients, one could do that too from this equation.